Okay, here is section 1-5, finding the probability of independent events and dependent events. So just like other situations in life, two events that can occur without affecting the other would be considered independent events. Sorry about the formatting on here, something went astray when I printed, so I think when I saved it as the PDF. So, can occur without affecting the other. So a really easy example of that is I can go to Taco Bell and buy a beef burrito, and you can go to Taco Bell and buy a taco, and the two things have no effect on one another. Okay? It's a really simplistic example. So the probability of those events, if they are independent events, then the probability of both of them occurring would be the probability of A times the probability of B. Okay? So for example, in a football game, 50 of 75 male fans and 40 of 50 female fans said that they favor the new team mascot. If one male and one female fan are randomly selected, what's the probability that they both favor the new mascot? So for males, you have a 50 out of 75 chance of saying that you favor the mascot. And for females, that would be a 40 out of 50 chance. You're going to multiply those two together, the 50s cancel out, and you would get 40 over 75. You're always going to reduce those down, of course, so you would get 8 out of 15 chance that those two people that you chose, one male and one female, so this is an and situation because it's both are in favor of the mascot. Okay, a survey found that 46% of parents surveyed say that they read to their children at least once a week. If 3 parents are selected at random, what is the probability that this should be a 3, will say that they read to their child once a week? Okay? And they're independent. It doesn't matter what the first parent says as to what the second parent says. So the first parent has a 46% chance of saying that they read to their children once a week. The second parent has the same possibility, and so does the third. The other way you could do this, of course, is 46 over 100 times 46 over 100 times 46 over 100. So I'll give you the answer both formats. So if you did it as a fraction, that actually reduces to 23 over 100. And it's the same to the third power. So that would be 12,167 over 125,000. Excuse me, that would be 50 to the third. Okay, that's one format. If we did it the other way and we just multiplied 0.46 to the third power, we would get 0.097336 or 9.73% possibility. Pretty low possibility, by the way, that all these people are reading to their children. I would love to see that percent much higher. Okay, so during each day of the week, actually this one we're going to skip. You can skip this one on your work. Okay? Again, the formatting got kind of messed up down here at the bottom. For dependent events, so now if independent events happen when the two events do not affect one another, you could logically say that dependent events do affect one another. So they are two events where the outcome of one affects the other. Okay? So an example of that, let's go back to the example. If I buy a burrito and a taco and I bring it into the classroom, and Hannah decides that she's going to have one, and so does Paveen. Well, if Hannah takes the taco first, now she's directly affected what Paveen can have, right? If she's taken the taco, now that's not an option for Paveen anymore. Okay? You also have something called conditional probability. And that's the probability that B will occur given that A has already occurred. Okay, on to page 2. So probability of dependent events looks like the probability of the first event times the probability of the second event given that that first event has already occurred. Okay, and that's denoted by that line in between the B and the A. Okay, so the table shows 200 registered college students. What's the probability that a randomly selected student is female? So let's first total up what we have. Total part-time workers, we have 140. Full-time workers, we have 60. We know that we have 200 students total. 140 plus 60 is 200, so we're okay. Female students, we have 80 that work part-time, 40 that work full-time. So that gives 120 females and 80 males. That still totals 200. So we know we have all of the college students that we're talking about. So the chances that somebody is going to be female, if we just choose one student out of 200, there are 120 students total, or total females, over 200 students total. So that is going to reduce to 3/5. Okay. Now, if somebody is female and a full-time student, okay, if that person I choose is female, then what's the chance that that person is going to be a full-time student? So now there's only 120 females to choose from, and 40 of them are full-time students. So if I did choose a female, now the chances that I pick a full-time student are 1 out of 3. Different probabilities going on, okay? You randomly select a card from a deck of 52 cards. What's the chance that the first card is a heart and the second card is a club? Nice drawing. And the second card is a club if you replace the first card before selecting the second card. So we first start with 52 total. How many hearts are in the deck? There are 13 cards from each suit. We take a heart and now we put it back into the deck. Okay? So now we still have 52 cards. And now what are the chances that you will choose a club? There's also 13 clubs in the deck, right? Each of those reduces to 1 out of 4, 1/4. So the chances that you'll pull a heart and then a club would be a 1 out of 16 chance. Now how does that change if we don't replace the first card? So we still have a 13 out of 52 chance of taking a heart, right? But now I haven't replaced that card. So now I've only got 51 cards in the deck. But how many of them are still clubs? There's still, assuming that we pulled a heart this first time, there's still 13 clubs in the deck. Okay? So now that reduces, so this is the big difference. We decreased our total number of cards by 1 because now I did not replace that card and put it back in and make it a full deck. So this would be 1 out of 4 times 13 over 51 to get 13 out of 204 chance. Okay? Sometimes it's easier to use a tree diagram to, sorry about that, Bryce came in and thought I was talking to myself. Okay, so you and 2 friends go to the same store at a different time to buy costumes for a costume party. There are 15 different costumes at the store, and the store has at least 3 duplicates of each costume. What is the probability that you choose different costumes? So let's say there's witch costume and a cat costume and a dragon costume, okay? So I've got 3 that I'm choosing from. There's 15 different kinds. So out of 15, whoever chooses first gets a 100% chance of choosing a unique costume. The second person, now that that costume's been chosen, they can't choose it again. So now they only have a 14 out of 15 chance. And that third person, now those first two costumes have been chosen, they can't choose them again. Okay? So now when you calculate that out, you can certainly cancel if you can. So we'd have 13 times 14, which is 182. And we would have 15 times 15, which is 225. If we change it, you could leave it like this. If we change it into a percentage, you would have 80.9% chance that you will all pick unique costumes. Okay, so going on to example 7. Sometimes it's actually easier to use tree diagrams to do these. Hopefully you don't have to do those very often. Sometimes it helps you see what you've got. So usually that's going to come in example 8 and 9 when you've got percentages going on. That's when the tree diagrams really help you kind of lay out what's going on. So suppose your area has 8 different internet service providers and you and 3 friends randomly select your own ISP. What's the probability that you all choose differently? Okay, so you being the first one, there's a 100% chance that you're going to pick a unique service provider because it's only you choosing, right? Once yours is chosen, it can't be chosen again. So the next person has a 7 out of 8 chance. Third person has a 6 out of 8 chance. Every time one is chosen, the percent that you're going to choose what you want, or a unique one, is going to go down. So we can go ahead and cancel. And so we would get 21 over 32. You could also divide that and make that into a percentage, and you would get 65.63% chance. Okay? On a quiz, I would take either one of those. It's an acceptable answer. Okay, so 8 and 9 is where I would actually recommend you doing just quick factor trees. So on a manufacturing line, 20% of all the items produced are defective. Although all the items are inspected before they are shipped, 10% of the items are incorrectly classified as either defective or not defective. What percent of the items will be classified as not defective? Okay, so let's just start with half. What do we know? We know that items are either defective or not defective. Okay, and we know that 20% are. So if 20% are defective, then we know that 80% are not defective. Although the items are inspected before they shipped, 10% of the items are incorrectly classified. So 10% are incorrectly classified. That's a 10%, which means 90% of them are correct. On both ends, whether they're not defective or actually defective. Okay? They're incorrectly classified 10% of the time. They're correctly classified 90% of the time. Okay? So now we just need to figure out which ones will be classified as not defective. So let's go ahead and highlight which ones out of here we're looking for. So what percent of the items will be classified as not defective? Okay, let's start down here. So if something is not defective, it really isn't defective, it's really good to go, and it gets classified correctly, there'll be 80% of them, and 90% of the time they're classified correctly as not defective. So we need the original 80% times 90% of the time we can go with that. It's classified correctly. However, for the defective ones, 10% of the time they're incorrectly classified as defective. Okay, so for that we need 0.2 and 0.1. So if we multiply those together, we get 0.02 and 0.72. So if we add those up, we've got 74% of our items will be classified as not defective. Okay? Sometimes with the tree diagram helps you lay it out. Highlighting it helps you really look at what you need. Okay, let's do the last one, and that's it for this section. So, high school basketball team leads at halftime in 60% of the games in a season. The team wins 80% of the time when they have the halftime lead, but only 10% of the time when they don't. What is the probability that they win during the season? So let's just start with what they know. So they lead 60% of the time. They're behind 40% of the time at halftime. Okay? When they have the halftime lead, they win 80% of the time, which means they must lose the other 20% of the time. But when they're behind at halftime, they only win 10% of the time, which means, by default, they must be losing the other 90% of the time. Okay? This is where this really works. So, what is the probability that they win a game during a season? So if they're in the lead and they win, you've got that probability. If they're behind, they still can win, right? A lot lower possibility that that's going to happen. But you would have 60% chance times an 80% chance. And we'd add that to when they're behind, it's only a 40% chance that they win. And only a 10% chance if they're, 40% of the time they're behind, there's only a 10% chance that they're going to win after that point. So that would be 0.48 and 0.04. So total you've got 0.52 or 52% chance that they're going to win any given game. Okay. All right, that's it for section 1-5. 1-6, I found a cute little video for you. It's on mean, median, mode, and range. You'll have another one for standard deviation. And so you will not get to listen to me for section 1-6. Okay, thanks.